Hello friends and welcome back. So now onwards we will start a new topic called finite element analysis. So this is the portion of computer aided design. So if you are following GTU, then you will be glad to know that I will cover almost all the topics of FEA chapter from this GTU syllabus. So as far as our GTU syllabus is concerned, we will try to cover all the topics which are given in our syllabus, right? And if time permits, then I will also try to explain extra concept of this FEA. So today we will have a introductory lecture. So try to watch this lecture because this will be the base for the upcoming video lectures, right? So please watch this lecture till the end. If you have any doubts, then you are free to ask me. And please subscribe to my channel if you are not subscribed. It means if you are new, and you can share this video if you are finding this video helpful, and please make sure that you hit the like button. So now without any further delay, let's get started. So now before diving into our topic finite element analysis, let's produce or let's create a background which help us to understand that what is finite element analysis, or where is a finite element analysis be used, or how it is used, right? So for that, I assume that till now all of you have studied the balancing of rotating masses and balancing of reciprocating masses. So I hope you know that means how we were balancing the rotating masses and reciprocating masses. Now let us consider that we are dealing with balancing of rotating masses. So now try to recall that how we were balancing the rotating masses, means which are the ways that by which we can balance the rotating mass. So first was by analytical method, means we were balancing the rotating masses by analytical method. So I think now you can recall something. And the second part is by graphical method. Don't worry, any of the concept of rotating masses will not be used in FEM. We are just creating a background which help us to understand that what is FEM or FEA, finite element analysis or finite element method. Now what we are doing in analytical method. So I hope you know that we are what is the analytical method? Means in analytical method we are just directly putting the values of the variable in the given formula. Means suppose that we are balancing the unbalanced force. So here this is the vertical component is 0 and this is the horizontal component we are taking 0. So what we are doing, I am showing the balancing of vertical component. So here we have mr omega square sine theta 1 plus mr means mr1, then mr omega square sine theta 2, and so on. So I hope you are recalling these terms. So we were just putting the values of m, r, omega in this equation and finding the values of theta 1 and theta 2. Means whatever we want to find, we can find by putting the values in this equation. But problem was what? Problem with analytical method is we have to follow a lengthy procedure. Means if you are solving the balancing of rotating masses by analytical method, then we have to follow a long procedure, a complex procedure. Now what we are doing in graphical method? In graphical method we are just drawing a force polygon like this and joining this remaining portion, if you know this part, right? We were just drawing the force polygon and we are measuring these vectors and finding the unknown values. So I want you to tell me that among these two methods, which was the easiest method you found? Obviously this graphical method, because it is easy and a very little steps we have to follow in order to get the answer. But what is the basic difference between these two methods? Just think. So the difference is what? In this analytical method we are getting the exact answer. If you know that exact answer we are getting. But what with graphical method? With graphical method we are getting approximate answer. approximate answer means nearer to this exact answer, right? And the easiest method was this graphical method. So I want you to think, means if you have a complex situation or complex problem in balancing of rotating masses, then means real life problem. Let us consider you are balancing a unbalanced mass in a real life problem. Then which method you will prefer? Will you prefer this method, analytical or graphical? Obviously graphical. Why? Because there are only less steps and you are getting the answer very fast, very rapidly, but you are getting the approximate answer. So in every engineering problem or any real life problem, what we do, we try to find the answer which approximate our exact answer. Means we don't go for analytical method to find the exact answer. We go for approximate answers. Why? Because if we are trying to find the exact answer by analytical method of any real life problem, then I am sure that you will end up in the hospital, right? So I am just joking. So it is very easy to go for analytical method in real life problem. So what we will do, we will go for approximation method. So this concept, finding the approximation answer, is used in FEM. So FEM is a method which help us to find real life problems in approximation answer way, right? So in these methods we will find the solutions for the real life problem in approximation manners, not exact manner. Means there is a certain steps in order to find the approximate answer. Means we cannot just go and say that yes, if the exact answer is like 5.5, then you can't go and say that let's write 5.4, this is our answer. No, we have to follow certain steps to get this approximate answer. So these steps are included in finite element analysis or finite element method, right? So we created this background that we have to find the approximate answers. Now, as this name suggests, what you can say means what are the steps in finite element analysis in order to solve the sums? Yes, this finite element means we have to create finite elements of a big structure and we have to do some analysis on that small elements. Means our finite element analysis works on the famous principle called divide and rule, right? Divide and rule. That means we will derive our whole component, complex component, into small known elements, and then we will analyze, or then we will follow some procedure to find some unknown values on that element, and then we will do some assembly of that elements in order to find the answer for whole component, right? So we will follow these steps. Now we will take an example and we will understand that what we will do in finite element analysis. Now let us consider a sheet metal. So here we have hole, right? This is the hole. Now I am giving a question to you, that, or I am asking a question that I want to find the area of this sheet. So please pause the video and think how we can find this area, because if you are successful in thinking that how we can find this area, then the 50% of today's topic is completed for you, right? So just try to think and pause the video. Now what we will do, so as the name suggests, what we will do, we will this principle works on divide and rule. Divide and rule. So we will divide this whole component into known shapes. So let us say this is our first element, first shape. This is our square or rectangle. Then this is the second, this is our rectangle, and this is the third, let's say triangle, and this is the circle, let's say fourth element. So what we will do, we will find the individual areas of these elements, element 1, element 2, element 3 and element 4, and at last we will do the assemblies of these 4 elements. Now I am using the word assembly. Now why I am using the word assembly? Why I am not using the word joint? Why I am not using the word joint? Because if I am using the word joint, then it means that you are joining the area of this whole, right? But what we have to do, we have to subtract this area of the whole. So to generalize that, we will use word assembly. Means we will assembly these all the four parts in order to find the area of this complex sheet metal, right? So now remember, use word assembly, because joint means we are adding the area of the whole also. So use assembly word, right? So I hope you got the idea that what we have to do means we have to divide the complex structure into small known element, and we have to do some analysis on that in order to find the answer of the complete structure. Right? Now we will move forward and see that what is elements and what are the nodes, because this is the main part or the heart of this chapter, that elements and nodes. You will play with these words in near future, like elements, nodes, etc. Right? Now again we will take a complex shape or structure, right? Now I want to find the same question, that I want to find the area of this complex element. So what I will do? No problem, I will divide this structure into small known elements. Just observe me. Right? So what I have done? I had divided all this area into small elements. So this is element 1, element 2, element 3, element 4, and so on. Now, so we can write these small regions as elements. So the elements are what? Small regions. And these elements which are meeting at the point is called nodes. So the point at which these elements are meeting is called nodes. I am repeating again, the points or the regions at which these elements are connecting each other is known as nodes. These are the nodes. And in finite element analysis, all the procedures, all the calculations are done on these nodes only, right? You will understand that how we can calculate, how we can find the stress, strain, or different types of problems on these nodes. There are certain procedures we will follow in upcoming videos, right? So what are the elements? These small regions called these elements, and the point at which these elements are connected with each other is called as nodes, right? So we will take another example. Suppose you have a step bar. Right? You have this step bar. All of you have solved this step bar problem in previous semesters in when you are dealing with MOS subject, that means mechanics of solid or strength of materials, like, right? So this is our bar. So what we will do, we will understand this concept of breaking the whole structure into elements and finding the answer. Yes, so there are certain rules by which we can place the nodes at different points. So now we have to find, let us say, forget this example, now just concentrate on this example. Suppose you have a taper bar. Now you want to find the, let's say you want to find the stress on this taper bar. You have the force applying at this point. So what you will do? Same concept. We will first divide this whole complex structure into small elements. So we will divide it 1 and 2. Now remember this point, that the more number of elements, the more accurate answer you will get, right? Means if you are dividing the elements into n small elements, then the number of elements will give you more approximate answer, more close to our exact answer. Less number of elements, less approximate answer. More number of elements, more approximate answer. But that more number of elements will also come with complex procedures. As we have to do, as we have to solve these sums on our with pen and paper, so we will try to divide this element into less number, means we will try to divide this component into less number of elements, right, to reduce the complexity. So let us consider I have divided this taper bar into 3 elements, 1, 2, 3. Now how we can number the element? So element number is always represented by the circle. So when you have a number with circle, that represents the element number. Element number, right? Now I have explained you this, the concept of nodes. So what was the concept of node? The point at which the elements are meeting is known as node. So here you can see these two elements are meeting at this point. Here you can see these two elements are meeting at this point. Here we have a boundary condition. Why we have kept the node here, we will see. And here also we will have a element. Why? Because this element is connected with this fixed structure or fixed portion. So we have how many nodes? 1, 2, 3 and 4 nodes, right? So number without circle indicates the node number. These are the node number. And always remember, this will be the pattern of numbering the nodes. You can't number the node as node 1, node 2, node 3, node 4. This will change the whole answer. So always try to number the node in this way only. That is 1, 2, 3 and 4. You can number the element in any manner. You can place one element, second element, third element, but don't change the node number, right? So what you are getting? You can say that this taper bar is resembling our step bar, like means see here. Let's say our taper bar, I am drawing the same object, I am drawing the same bar. So we have this type of element, means we have divided our taper bar into small element, and this taper bar is resembling our step bar. So I am using bar, right? Because in this chapter we have different beam elements, bar elements and so on. So now we are dealing with bar only. So I have divided, means I had divided this step bar into I had divided this taper bar into 3 small elements as this. So I will draw FEA model. So see how this FEA model is drawn. So see, just we have to draw a single line. Now this element 1, these are the nodes 1, 2, 3 and 4. So node 1 is here, node 2 is here, node 3 is here and node 4 is here. So 1, 2, 3, 4. First element, second element and third element, right? This is the simple model of FEA. Means when you are solving the problem of FEA, then you are not required to draw this whole component. You just need to draw this FEA model. This is called the FEA model. So where are the nodes? This is node 1, 2, 3 and 4, right? Now we will discuss means how to place the nodes. Rules for placing the nodes, means why I had placed the node here, why here and why here, right? So we will see. In similar way, this is also our step bar. Okay, first we will discuss the rules and then you will yourself only keep the nodes, right? So these are the 4 basic rules by which we can place the nodes correctly. So first is what? Place nodes where cross section changes. So you can observe here, as we have divided this taper bar into this type of elements, so we can resemble this taper bar into a step bar, right? How we have converted this taper bar into step bar, you can understand this in detail in the upcoming videos. But for for instance, let's say we have this taper bar, we have this step bar. So as our first rule suggests, that place nodes where cross section changes. So you can observe here our cross section changes, right? This is the first bar and this is the second bar. If we consider this component is made of 3 bars. So here at this point our cross section changes, so we are putting a node here. So now what about second? Place nodes at boundary condition. Now boundary condition means what? The place at which you know the condition. So this is the place where you know the condition, means at this point the displacement of the node or the deflection of the node will be 0, as this end is fixed. So placing the nodes at this point. Now here also the cross section changes, so we are keeping this node. Now suppose that here we have a force. Here force is applied F. Now what is third rule? Place the nodes where material changes. Means suppose that you are given, or you are given in the equation that this section has the Young's modulus as U1, E1, and this section as E2. So you have to place the nodes in between where the materials changes for the bar or for the component. Then fourth is where, or fourth is what? Place nodes where unknown values are to be found. Now here you are asked to find the stresses at point, this point, right? If you are asked to find the stresses at this point, then you have to keep the node at this point. Now for example, if in the question it is given like this, the force is given like this, then what you will do? Then you have to keep the node here, means you have to discretize or you have to divide this component from this element. So this is our element 1, element 2, element 3, right? So we have kept the node at this point. So this is the node, this is the node, and this is the node, right? Node 1, node 2, node 3, and node 4. So I hope you got the idea. So these are the 4 important rules which you have to keep in mind in order to solve the sums of this bar element. Now we will see the element connectivity table. Now observe me that how I am drawing the FEA model. Suppose you are asked to find the stresses for this step bar and you are given the force here, right? So see how I am drawing the FEA model, right? Keep the rules, the 4 rules of placing the nodes in your mind. So I am drawing the FEA model. So first was the rule, which was the first rule? Place the nodes where the cross section changes. So here our cross section changes. So node 1, here also our cross section changes. Node 2, here also our cross section changes. Node 3, right? And also here our cross section is different. So here. Then let's say this is node 1, node 2, node 3, and node 4. This is element number 1, element number 2, element number 3. So 1, 2, 3. Right? The second rule was what? Place the nodes at the material changes. Third was place the nodes where boundary conditions are given, and place the node. Fourth was place the nodes where the unknown values are to be found. Now this is the FEA model. This is the model for bar element. For beam element it is different, right? So we are writing element connectivity table. So this, in this column I will write element, and in this column I will write nodes. Element node connectivity. So element first. In first element, how many nodes are here? So here it is node 1 and node 2. So node 1, node 2. In this second element, how many nodes are there? Node 2, node 3. So second element have node 2 and node 3. This third element have node 3 and node 4. Third element have node 3 and node 4. Right? This table is useful to draw the global stiffness matrix. So please understand this. I will explain you again. This is our FEA model. This is our FEA model. Right? Now I am preparing this element node connectivity table. So element in one column and node in the other column. So we will see in the first element the node, how many nodes are there? Node 1 and node 2. So 1, 2. In the second element we have 2 and 3 nodes. 2 and 3. In the third element we have 3 and 4 nodes. 3 and 4. Right? As we are dealing with only bar element, then how many degrees of freedom for bar element will be? So bar element will have 1 degree of freedom. Now what is 1 degree of freedom? Now suppose I am representing this element number 1. So this is element number 1, node 1, node 2. So what is degree of freedom? We will see. So here the force is applied at this point, at node 4. So obviously as the force is applied, so there will be a deflection in node 3, node 2, node 3 and node 4. There will not be any deflection in node 1, as node 1 is fixed to this end, right? So there will be a deflection in node 3, node 2, node 3 and node 4. As the force is applied in this direction, so obviously this node 2 will move in this direction, right? Now suppose if I am applying force in this direction. So it is obvious now this node will move in this direction. So in how many direction this node 2 is moving? 2. Am I correct? No. This is moving only in x direction, but it is moving along positive x or negative x, right? That means node 2 is moving in one direction and it will have 1 degree of freedom. So in case of bar element, we will have always 1 degree of freedom. Always remember, always keep this in mind. Now imagine, suppose we are applying force in this direction, then obviously this node will move here, right? Now you can say that node 2 or node have 2 degrees of freedom. Why? Because node can move in this direction and node can move in this direction also. So in this case we will have 2 degree of freedom, but in the previous case we have only 1 degree of freedom. So in bar element we will have 1 degree of freedom. So I hope you know the concept behind degree of freedom, right? So this was about degrees of freedom, element node connectivity table, and yes. Okay. Yes, okay. So we have almost completed the introduction, means overview of FEM. We will see what are the steps, what are the procedures to solve the sums related to FEM in the upcoming videos. In the next video, you will see that how to derive the elemental stiffness matrix, means what is elemental stiffness matrix. In upcoming video, in I think after 1 or 2 video, you will see that what is shape function, what is displacement model, what is local coordinate system, what is natural coordinate system, right? What is zeta and all that. So please stay tuned with me and subscribe to my channel if you have not subscribed yet, and please like this video if you have enjoyed this lecture, and please share this video as much as you can share, and if you have any doubts then please ask me in the comment section. So till then, have a good day and bye bye.